In this video, we're going to start solving exponential equations, and I'm going to start by reminding you about what you should have seen or learned in grade 11, and you're going to practice some of those. So the first key when you are solving exponential equations is to make sure that you can simplify or rewrite the powers so that they have the same base, and there should only be one power on each side. Okay, so right away I look at this very first one and I see that both of these can be written with a base of 2. So I'm going to do that. So the 4 can be written as 2 to the 2, and there's an x plus 5 outside. The 8 can be written as 2 to the 3. Now it also has a square root, so it's actually 2 to the 3 to the half, if you like, or 3 over 2. And then there's an exponent of 2x minus 6. Okay, so first step is to make them the same base. Once you have made them the same base, you can actually bring the exponents down. Okay, so if we look at our exponents right now, we have this and we have all of this. And so once we have the same base, we can say that this exponent must equal the exponent on the right-hand side. And we can do a little bit of simplifying with that. Okay, and then you're just solving a linear equation just like you know how. Go ahead and do that. Okay, and hopefully those steps make sense to you. So let's just summarize in terms of writing down some steps before we try another couple of them. Now, one of the first steps is to make sure that you have a single power on each side. So you're going to simplify to have a single power on each side. Then you're going to rewrite both of those powers so that they have the same base. Okay. And once the bases are the same, then you can bring down the exponents because they must be equal. And then it's just a matter of simplifying and solving. Okay, so let's go ahead and let's try B. Okay, so right away in question B, I see that I have a 36, and I know that that can be written as 6 squared. Okay, and then 216, I double check, and that actually can be written as 6 to the 3. Okay, there was nothing else to simplify there, so I went straight to step 2, rewriting both powers with the same base. Once they're the same base, I can bring down the exponents. Just watch your brackets and signs. And then just go ahead and solve. So you should definitely pause the video now and be able to finish this one on your own. Okay, so check your work there. Hopefully that one makes sense. And let's take a look at C. So C looks a little different because I see the 5, the 3, and the 1,215, and I don't seem to be able to make them all the same base. And your hint there is that you have to have a single power on each side first. So the first thing you have to do is you have to get rid of this 5. You need to divide it to the other side, and hopefully then you'll be able to recognize a number that can be turned into a power with the same base, a base of 3 in this case. So this is step number 1 here, where you want to simplify to have a single power on each side. Now, a lot of people might be tempted to take this 5 and to multiply it by the 3, but you cannot do that, right? Because the 3 has an exponent, and we always deal with exponents before multiplication following BEDMAS. So that's why you cannot do that. So the first step is to divide. And magically, when you divide 1215 by 5, you get 243, which sounds familiar and can be written as a base of 3. And you might just need to check on your calculator what that is. It's actually 3 to the 5, and that's where your calculator can be handy if you're not sure. And again, then I think you can solve the rest. So pause the video, finish it on your own, and double check your answer. Okay, so that's your quick little reminder from grade 11. Those are some of the ones that you should have solved in grade 11. And just before you practice that, I do want to make sure that you understand that these are all exponential equations. And how can you tell by looking at them that they're exponential equations? I hope it's obvious to you that the x that you're solving for is in the exponent. Okay, so there you have that there. Make sure you write that down, that little note. So if you want to do a little bit of practice now with the grade 11 ones, you could do these questions right now and pause the video and then just come back so we can continue on with our grade 12 skills. If you remember doing this in grade 11, then you might be able to hold off and do those all at the end. Okay, so as we enter our grade 12 knowledge now of exponential equations, I ask, what about something like this? Okay, and I hope your thought is we can't make those bases the same. 53 cannot be written as 5 to the exponent of something, and so therefore there must be another way. So what we do is we take the log of both sides, okay? And it's going to look like this. Okay, and you might have actually seen this before. It's possible that in grade 11 somebody did teach you how to do this, or in chemistry you did this, you just didn't know why you were doing it, okay? So the big reason of why we do this, obviously we can do it because we're taking the log of both sides, so that's okay, but the reason is because then it allows us to use the power law of logarithms to bring that x down. And so it becomes x log 5 equals log 53. So here we used the power law of logarithms. Okay, and then we can simply just keep isolating, so we know that then x is going to equal log 53 over log 5. And this is our exact answer, and then you can go ahead and punch that into your calculator and get an approximate answer as well. And you should get approximately 2.47. Okay, so that's the method. We're going to try a few more that are each a little more complicated or have different things to consider. Okay, so right here when I look at this one, I first double check and see if I can make the bases the same. And as soon as I see that I can't make the bases the same, I take the log of both sides. Okay, now this one's just a little bit different because when you apply the power law, you have that whole piece, 2x minus 3, that is going to come down, right? So just make sure it's in brackets and make sure we understand what that means. And that means that if this was a number log 10, that would have to, get distributed to both pieces in the brackets. Now, I am going to put a little star here, though, because I do want to let you know that on the side here, log 10, remember, is the same as a little 10 there. So 10 to the what equals 10, so you can verify this on your calculator, but log 10 actually equals 1. And while we're at it, just a couple of other ones. Think about then, what would this be? So 10 to the exponent of what equals 1? That would be 0. These are a few special ones. Check another one, log 0 on your calculator. So 10 to the what equals 0. That does not exist, right? That has no value. Okay, and again, because when x is 0, that's not part of the domain of a log function. So that's the reason for that. So that's just a little aside that you might want to write down. Okay, so let's continue then with our solving. So like we said, this one simplifies really nicely though, because log 10 just equals 1. And so what we really have is we have 2x minus 3 equals log 1500. So 2x is going to equal log 1500 plus 3, and x is going to equal log 1500 plus 3, all divided by 2. So that's exact. And then you're welcome to just punch that into your calculator to get an approximate answer. We are going to solve with exact values, but it's much easier to compare with your neighbor and make sure that you did things correctly if you also approximate as a decimal as the very last step. Okay, so you should get 3.09 there. Make sure you can punch that into your calculator. Okay, so in example 2, we're going to make things a little bit more complicated here. And we have that extra term right here in front. Note, we cannot multiply that into the 5x. Just following BEDMAS there, you always have to do exponents before you do multiplication, right? So no multiplying or dividing here. So again, we can't make them the same base. So our first step is going to be to take the log of both sides. And just making sure you can see it correctly. I'm writing it out like that. Now, in order to deal with this left-hand side, you'll notice that we have two things in the brackets. They are being multiplied together, and so we're going to have to use our product law here to separate them. So that left side becomes log 2 plus log of 5 to the x equals log of 10 to the x plus 1. So we can't bring this x down here until we have separated it because the x is not part of both pieces. So you must use the product law first. So then we can continue. Remember, we take the log of both sides so that we can bring those exponents down and use that power law. So this becomes x log 5, and we have x plus 1 log 10. And again, log 10 is just 1, so that right-hand side simplifies to just x plus 1. Okay, but if it wasn't 1, you would have to distribute it to both terms. Okay, so now this one's just a little bit more complicated because I do have x's on both sides. So what we want to do is we want to move all the x terms to one side and all the number terms to the other so that we are able to isolate for x. So I'm going to keep that term on the left. So we have x log 5. And then I'm going to take this x and move it to the left. Of course, it becomes subtract x. On the right-hand side, we have our 1, and our log 2 gets moved to the right-hand side as well. On the left, now we need to isolate x, so we're going to common factor x out. We're left with log 5 minus 1. And so that then we can get x by itself by simply dividing 1 minus log 2 all over log 5 minus 1. Okay, again, that's our exact answer. And then you can go ahead and punch that into your calculator to get a decimal. And just double check your work. Make sure you have the right answer here. You should get approximately negative 2.32. Okay, so in our next example, this one looks a little different, and I hope when you get to practicing that you can recognize these ones. These ones are what we call quadratic exponential equations. So we know when we solve quadratics, we look to factor, and just to help you to be able to see it like we did with our trig functions, we're going to let y equal 2 to the x, so this power function right there. And thus, this equation becomes y squared minus y minus 6 equals 0. Okay, as we do with all quadratics, we're going to factor that. Obviously, if it didn't factor, you could use the quadratic formula. So that factors to be y minus 3, y plus 2 equals 0. And of course, we have two solutions, y equals 3 and y equals negative 2. Okay, but just like with trig functions, you're not done yet, right? Now let's go back to our exponentials. So we're going to replace those y's again with 2 to the x. Okay, so on the left here, we're solving 2 to the x equals 3. So that's a nice simple exponential equation. And on the right here, we're solving 2 to the x equals negative 2. Okay, so we're going to solve both of those small ones. We'll start on the left. We're going to take the log of both sides. We do that so we can bring the x down. And thus we know our exact answer is x equals log 3 over log 2. Okay, and you could always approximate that as well if you want. Now on the right, we go to do that, and let's take a look at what happens. Okay, so following our usual steps, we get to this point right here, but it's important to note that when you go to punch that into your calculator, this is going to give you an error, right? Okay, let's return just to the original for just a minute before I took the log of both sides. Remember that this is asking 2 to the what equals -2. Well, think about that for a minute, right? Exponential functions, or 2 to any exponent, will never equal a negative number, right? Powers only equal positive numbers because the range of the exponential function is y is greater than 0, right? There are all positive values there. Thus, when we are solving this, x has no solutions from this point. Okay, and we can think of it in a variety of ways. The first way, 2 to the something will never equal -2. We can also say that the range of the exponential function is y is greater than 0. Or we can even look down to the logarithmic function over there, and log -2 does not exist, right? Because the domain of the log function is x is greater than 0. So all of those things sort of mean the same thing, just referring to different aspects of which function I'm taking into consideration. But the bottom line is we have no solutions from there, so this question only has one solution. Okay, so you're going to practice all those types of equations. Okay, and our last question, I just want to introduce you to one type of application question, and hopefully you did see these ones before in grade 11. So here's what I would call sort of the general equation for modeling exponential functions, or exponential models, if you like. It can also be written like this one on the right here, and I'm just going to tell you what all of the individual pieces mean. Okay, so our y in both scenarios would be our final amount, and our a is the initial amount. I think that should make sense to you. The b is our base for the question. So whether that be a half-life and the base would be a half, or if the scenario is doubling and the base would be 2, or the scenario could be tripling, base is 3, and so on, okay? So then oftentimes it's just written as one exponent over here, x, and that could represent time in years. But sometimes it's also written as t over something like h, and that would be sort of what I would call the half-life time, or if it was doubling, the doubling time. And the time is just the overall time. So let me show you what I mean by looking at this question. So in example 4, it says the initial amount of caffeine in Helen's body is 20 milligrams and the half-life is 4 hours. Okay, so that means it gets cut in half every 4 hours. Okay. How long does it take to reduce the caffeine down to 4 milligrams? So let's start by writing our general equation. Okay, so there's our general equation, and let's see if we can interpret that, right? So we're looking for how long it reduces down to 4 milligrams, so 4 is our final amount. I hope that you can see that that means A is our initial amount, which is 20. Now, because it's a half-life question, that means the base is half. Okay, we are trying to find the time, so we're trying to find t, and that half-life time is 4 hours, okay? So sometimes that's just a 1, and that's why then you just have one exponent, like in this equation at the top. But in this case, it's being cut in half every 4 hours, so we need to have that 4 in there. Okay, so this is an exponential equation, and we're going to solve it using our skills that we've been going over in the rest of this lesson. Hopefully you can see that your first step would be to divide the 20 over to the left-hand side. So we get 4 over 20 equals 1/2 to the t over 4, and that does simplify to 1 over 5 equals 1/2 to the t over 4. Then I'm looking to see if they can be made the same base, and they can't be made the same base, so then I'm going to take the log of both sides and then solve for t. So from that point, I hope that you can pause the video and try some of those steps on your own, and you can go to a final answer that is in decimals once you get to your last step, so that we can make some sense out of it. So pause the video and try that. Okay, so I've taken the log of both sides, and now I'm just going to isolate for the t right here. Okay, so therefore, it will take approximately 9.29 hours to reduce to 4 milligrams of caffeine in the body. So we will practice a few of these today along with our exponential equations. So I have one here that you can try, and the answer is right there, and then you can go ahead and start some of your textbook practice.